Hello everyone and welcome to this video. Today we're going to cover transients for electrical engineering principles and applications, and this is part of chapter 3. As you can see, we're going to go over the outline. The first outcome is going to be solve first order RC or RL circuits, understand the concepts of transient response and steady state response, relate the transient response of first order circuits to the time constant, and we're going to discuss also second order circuits. So let's start with transients. Transients, the time varying currents and voltages resulting from the sudden application of sources, usually due to switching, are called transients. So it's the time varying of both current and voltage resulting from the sudden application of sources. And so by writing circuit equations, we can obtain integral differential equations. And so these will include integrals and will include differential equations in one equation, and we can, through manipulation of the equations, we can write them as a single differential equation of second order or maybe third order, depending on, it's mostly the second order circuits that are gonna be mostly usual that we're gonna have second order circuits. And so let's talk about transients. As you can see, we have capacitance charged to V0 period to t equals 0. And so Vc, as you can see here, is the voltage across the capacitor. And also we have here a switch which is closed at t equals 0. After t bigger than 0, it's closed. If t is smaller than 0, then it's going to be open. And we have a resistor. And this can be compared to the fluid flow analogy. So a capacitor is discharging through a resistance, and it's fluid flow analogy. The capacitor is charged to V0. First of all, the capacitance or the capacitor is charged to V0 period to t equals 0. So the capacitor is already charged before it's closed, before the switch is closed. And at t equals 0, the switch closes and the capacitor discharges through the resistor, as you can see. And when that happens, it's like opening the gate for the water to flow, okay? And the water flowing is just compared to charging the capacitor or having a charged capacitor. At a full tank is compared to having a charged capacitor, and opening the gate for the water to flow is just compared to opening or closing the switch for the current to flow through the resistance. And so discharge of capacitance through a resistance, as you can see. So here we have capacitance charged to V0 period to t equals 0. Okay, so the capacitor is charged, and we can write KCL, Kirchhoff current law, at the top node with the switch closed. So let's consider this node, okay, and then we take IC, which is the current through C, plus IR, which is the current through 0. Okay, so we are assuming the current is going up in the capacitor, and also we are assuming that the current is going down in the resistor. And so if we apply the rules for IC is basically equivalent to C times the derivative of the voltage Vc over dt. That's what IC is basically. That's what IC is. And so IR, we know that IR from Ohm's law is just Vc over R, which is the voltage at C over R. And so when you substitute these values, we get a first order linear differential equation, as you can see. And if we divide by R, or if we multiply by R, so we have this term only including the variable Vc. We're going to have RC dVc over dt plus Vc of t equals 0. And equals 0 because we don't have any voltage sources or any way of, we don't have any voltage source, so that's going to be equal to 0. That's according to the Kirchhoff current law, which is KCL. So this can be written as dvc dt over dt equals minus 1 over rc vt. And that's basically a separable differential equation. So we can integrate both sides, or we can take v of t to the other side, so it's down, and we take dt to the other side and we integrate both sides. This will give us basically a differential equation of the form vc of t k e to the st, and s and k are constants that need to be solved for. And so the solution of equation 2 is a function with the same form as its first derivative, an exponential. And this can be easily shown true by basically substituting, or basically the only function that its derivative can be equal to itself without a derivative is the exponential function. And a derivative of the exponential function is basically the exponential function itself. And that's basically what we have here. That's the function here. And if you substitute an exponential function, we're going to get back the exponential function. But the difference is we're going to have some constant in k and s that are going to be determined by us in the equation. And so k and s are constants to be determined. And so if we substitute equation 2 and equation 1, if we substitute these two equations, substitute k e to the st into the original equation, so we take the derivative, we're going to have basically rc, and then the derivative of ks e to the st is just ks e to the st. Okay, just multiplying s by the whole thing, and then we add it to vc here, which is k e to the st, as you can see, and this gives us this function that we can solve for. And so we can take k e to the st as a common factor, and then we have, as you can see here, discharging of a capacitance through a resistance. We can take k e to the st as a common factor, and we have rcs plus 1 times k e to the st equals 0. And so this basically indicates that rcs plus 1 is equal to 0. And so from that we can say that s is equal to negative 1 over rc, and that's basically what we call it the time constant, or tau. This is called, rc is called tau, and when you substitute it in the equation we got this value. And so let's talk about now the k. How can we find the k? So the voltage immediately after the switch is closed is vc 0 plus. 0 plus means the voltage after the switch is closed, and so that's gonna equal to the voltage across the capacitance, or the capacitor, which is v naught. As you said, it has been charged before, and so vc after the switch is closed is equal v naught. And if we substitute 0 into the equation k e to the st, we're gonna get k e to the 0, which is basically k, which then indicates that k is gonna be equal to v naught, which is the initial voltage that the capacitor has been charged with. And thus we can say that vc of t equals v naught e to the negative t over rc. And since the voltage across the capacitor cannot change instantaneously, current would be infinite. Yeah, so the voltage across the capacitor cannot change instantaneously, and this means that the current would be infinite if it changes instantaneously, and that's not possible. The current changes like in a discrete way, since current is basically electrons flowing. The electrons are discrete, they are not continuous, and so that's why the voltage across the capacitor cannot change instantaneously. And so now let's talk about the time constant, which is here, it's the RC here. That's an important constant that was even given a name by itself. And so as you can see, RC is just tau here, and the time after one resistance value times the capacitance. And so voltage versus time for the current of figure 4.1, as you can see, this is the voltage versus time. Now with the switch is closed, the voltage across the capacitor decays exponentially to 0. And exponentially because the function we have it is in exponential form, and so it decays exponentially to 0. And at one time constant, the voltage is equal to 36.8% of its initial value, or 0.368 times its initial value. So that's the value of the voltage after one time constant, and time constant is just RC. It depends on the circuit and the capacitor. Depends on both of these. Depends on the resistance through the capacitor, or the resistance of the current flowing through the resistors, and depends also on the capacitor. And so it's important to note that the time interval T0 RC is called the time constant of the circuit. And after about 5 time constants, the voltage remaining on the capacitor will be negligible compared to the initial value, and we considered to be 0. After 5 time constants, the current or the voltage will be considered to be 0. Now let's talk about if you want to charge a capacitor. So charging a capacitor is now different than discharging a capacitor. So our first case was discharging a capacitor. Now we are discussing what if we are charging a capacitor with a voltage source. How would that be modeled? So what if you want to charge a capacitor through a resistor? Assume that that switch will be closed at t equals 0, and this will connect to the DC source to the current. So the capacitor is empty. It has no charge, no current, no charge on it. And we have a voltage source, and when we close the switch, at t equals 0, the source will start charging the current, the capacitor through the resistor. It's gonna go through the resistor and it's gonna charge the capacitor. And so we can apply Kirchhoff current law at the upper node when the switch is closed. And this is gonna give us basically the change of dVc over dt over time. And so we're gonna add that to also the current through the capacitor, okay, which is Vc minus Vs. Since when we are considering this node, we consider this node also, there are two currents. There is a current going through the resistor, and there is a current going through the capacitor. And so one current is going to be basically the current through the capacitor, which is C dV over dt, and the other current is, as we did here, is just the current through the resistor. And the current through the resistor is basically Vs or Vc is just Vc minus Vs over the current or over the resistance of the resistor. And so if you multiply both sides by R and we take Vc to the other side, or Vs to the other side, which is the voltage of the source, is constant, we are assuming that the voltage of the source is not changing, as constant the DC source, and it's not changing. And so we are having Vc by itself without any coefficients, and we are having the first derivative with coefficients which are Rc. And so here, if we solve this equation, we're gonna have the general solution to be as Vc k1 plus k2 e to the st. That's the general solution for such a circuit, and this is something you can memorize, or you can try to do by using some integration techniques that can be used, such as first order differential equations, multiplying by an exponential, trying to solve a first order linear differential equation. And so here we have three constants, which are k1, k2, and s. These are the three constants. And so we have here, as you can see, if we try to take the first derivative of this, is going to be k2 s e to the st. as you can see, K2 e to the st, and this is going to be substituted into the RC equation, and we're going to substitute VC into VC, like we're going to substitute the exact value into the equation. And so this will lead us to something like this. It's going to lead us to 1 plus RCS K2 e to the st plus K1, and that's basically from multiplying RC by S and also adding K2 from the VC, and taking common factors is going to lead us to this formula, and we're going to have K1 as by itself, individual, and so this will lead us to the conclusion that 1 plus RCS K2 e to the st is going to equal to 0, and K1 is going to equal to Vs. That's the conclusion that we can draw from this function. And so, and from that we can say that S is equal to -1 over RC and K1 is equal to Vs. And so we say the capacitor is initially uncharged. That's our assumption. So VC after the switch is closed is equal to VC after the switch was not closed, was open. Okay, and it's equal to 0. That's our assumption, that the capacitor is initially uncharged. So before the switch was opened and after it, the charge is the same and the voltage is the same, which means the voltage across the capacitor is 0. And so VC of 0 from the right equal to 0, equal to, if we substitute 0 into our equation, so if we put in Vs and we substitute 0 for t, we can have Vs plus K2, and this is going to lead us to K2 equals minus Vs. And so this gives us the equation Vc equals Vs minus Vs e to the -t over tau, and tau is just Rc. And that's basically a general solution for our problem, which is charging a capacitor. So when we charge a capacitor, the general solution is usually of the form Vs minus Vs, and Vs is the source voltage, okay, multiplied by e to the -t over tau, which is the exponential function. And now if we want to graph this, charging a capacitor, steady state after 5 time constants, as you can see, after 5 time constants, the capacitor is fully charged and it's in steady state. And after 1 time constant, the voltage is almost 0.632 Vs, which is 0.632 of the maximum voltage, which is the voltage source, or the voltage of the source. And so here there are 2 components of the VC. There is the steady state or forced response, which is Vs, and there is the transient response, which is minus Vs e to the -t over tau. So Vs here, as you can see, is the forced response, and there is the transient response, which is determined by time constants and also the voltage source. And this is the DC steady state. As you can see, the forced response, the transient response, and all of these are included in the equation. And so the steps used in determining the forced response for RLC circuits with DC sources are replacing capacitance with open circuits, replacing inductances with short circuits, and solving for the remaining circuit. As you can see, DC steady state. So if you have a circuit which is in DC and it's in steady state, so we are assuming it's either, so it's the capacitors are fully charged or not charged at all, but they are in steady state. So the charging is not happening, it's not charging or discharging, they are in steady state. And the same for the inductances, there is no current flowing, or the current is constant through the inductances, and which means that there is no change in the voltage across the inductance, and this could mean that the voltage through the inductance is 0, and so we can replace it by a short circuit. As for the capacitor, we can replace it by an open circuit since no current is flowing through that capacitor. And so we can see here a capacitor, and we can see an inductor, we can see some resistances and a voltage source, and we can see a switch here. And so here we have the voltage source and we have the resistances, as you can see. So we replaced, basically what happened here is we replaced the inductance with a short circuit, we replaced it with a wire, and for the capacitor we replaced it by an open circuit, as you can see, which is the VC right here. And so basically this is a normal circuit. We can use Ohm's law. Ix is just 10, which is the sum of the voltage source divided by R1 plus R2, the sum of the two resistances. Since they are in series, the equivalent resistance is the sum of them, which is 10, which gives us 1 ampere. As for Vx is just the current times the resistance, which is R2 times Ix, which is 5 times 1, which is 5 volts. And here are some other examples on DC steady states, which asks us to compute the unknown currents and the unknown voltages when the switch is opened or closed. And you can go ahead and try to solve these. And I'm not going to go through them, but let's summarize what we have went through so far. So summary of solving RC or RL circuits. The step involved in solving simple circuits containing DC sources, resistances, and one energy storage element, inductance or capacitance, are as follows. So 1. Apply Kirchhoff's current and voltage laws to write the current equations. That's the first step. We're going to apply KVL or KCL, Kirchhoff's current and voltage laws. And if the equation contains integrals, differentiate each term in the equation to produce a pure differential equation. So if you have integrals in the terms, we're going to integrate that in order to integrate the whole equation in order to get a differential equation with only pure differentials. And so then we're going to assume a solution of the form k1 plus k2 e to the st. And then we're going to substitute the solution into the differential equation to determine the values of k1 and s, and also k2. And then use the initial conditions to determine the value of k2. So k2 can be determined using the initial conditions, which are v of 0 and v of infinity. And then we're going to write the final solution. And that's all. Thank you for watching. I hope you benefited from this video.